but I will start with an overview of DuckDB. So DuckDB essentially exists because of this guy who went on the internet, went on a public forum and said that you shouldn't put your data in a database. It will only be slower and more frustrating, and that really hurt our feelings. You see, like especially if somebody like this Hadley Wickham, who is well known in the R world, says this, we thought we'd do something about it. Which brings me to the sandwich. Why is using a database frustrating and slower? Because the research field that Joran likes a lot has focused on this middle bit only in the last 50 years or so. We have tons of papers on join order optimization, and we have like 0 papers on client protocols. That's not true, we have 1. It's ours. But there's 1,000 papers on, like buffer management, and there's 0 papers on time from, a decision to use a specific system to actually running a query. Right? So what we realize is that we had to actually look at the end-to-end experience for databases. Like what is, what are the frustrations that people have? One of the frustrations, for example, is installation. I don't know if anybody's ever tried to get Postgres running from scratch, but it basically means that you have to go to a pg_hba.conf and change some parameters from Unix authentication to something else, and you have to add like actually listening to a socket instead of a port, instead of a socket in order to connect to it. It's a mess. This is this thing, right? Where people have only cared about, it works for me. So user experience, DuckDB is really about looking at the end-to-end for user experience. And one of the things that we realized that was ruining the user experience big time was this client-server paradigm, where basically, since I looked this up, since Sybase in 1984, everybody was kind of using client-server for databases, where we had a server and then some sort of shitty client protocol talk to a client, and basically that was the undisputed thing. But what we, and here is actually a screenshot from the paper that Mark and I wrote about how client protocols are terrible. Short summary is like at least 100 worse at least 10 times worse than netcut. That was the best we could do in client protocols. People ignore the fact that the most successful database management system on the planet with over 1 trillion active databases is SQLite. And you may not be aware of how many SQLite databases you are currently interacting with, but since you have a phone, I assume there's probably at least 10 of them. Because that's how phones work. Like, people don't talk about this a lot. SQLite, amazing system. Well, some questionable design decisions here and there, but it's extremely, extremely popular. The only downside of SQLite, I think, from the design perspective, is that's all about transactions, and who cares about transactions? And it's really nothing for analytics, right? But we care about analytics. We want to look at large data sets. It's an entirely relevant sector of the database market. Maybe it's slightly smaller than the transactional ones. I will admit to that. But SQLite, being a transactional system, I'm not sure actually whether you would agree to that, but it's a row major system of sorts, right? It's more about point updates. It has B trees. It claims to be sort of safe in terms of durability, but we have never looked at that. But it's not great if you want to put 1 billion rows into SQLite and start running aggregates. It's like end of story, right? So that's what DuckDB comes in. But the lesson from SQLite is that in process is actually good, because it simplifies some of these pains that people have been running into. In process means we actually link the database inside whatever process you want, and then lots of great things happen. For example, installation setup. You don't have to do authentication because you're already in the process. You don't have to talk to anyone. Data transfer becomes much faster. There's a ton of nice things to that. So enter DuckDB. DuckDB is a in-process OLAP database management system written in C++11 and proudly using Cmake to build. Okay, I fully agree with all the criticisms on Cmake. Don't get me wrong. being an old person, I have seen the world before Cmake, and it is a lawless wasteland that is so much worse that for me it's always very funny when people say Cmake is horrifying, because I agree with that. But then I feel like, have you got any idea what was before that, right? And another database system that will not be mentioned actually invented their own build system that generated autoconf scripts that then went through 3 layers of M4 macros in order to generate make files that were executed by make in order to build a database system with 1,000 or so source files. That is the world I grew up in, and I have to say Cmake solved that, but I admit there is room for improvement. Written in C++ 11. Of course, some people here might say, hey, hang on, why are you not using the latest and greatest C++? And the reason for that is that we want to be basically able to run anywhere. And anywhere means somewhere with a shitty compiler, and which is why we went for C++ 11, because it was sort of the best compromise between compiles on a shitty compiler, parenthesis GCC4-ish, right? Versus has features that we like smart pointers, period. DuckDB is a SQL system, and OLAP analytics, unlike these trivial transactions, are characterized by complicated queries. Okay, the queries that people write for analytics, they're generally horrifying, big, and use all the SQL features you've ever heard of in one query, because so in order to support those queries, DuckDB supports a lot of a huge chunk of whatever you are legally allowed to do in a SQL query. I don't know how to say that. There's a SQL standard, yes, but it's not really a good source. What people expect from a SQL system, I think, is a better sort of metric there, right? There is some ACID in DuckDB, but of course it's not really our core thing, and I will mention it again later. DuckDB supports transactions, which is in terms of atomic changes to your database, which is something that cannot be said for every OLAP system. Again, not mentioning another system. There's no external dependencies, 0. That was also something that we learned from the pain, or that I specifically learned from trying to get other people's stuff to run on servers at the CWI across the street, where Niels, our wonderful sysadmin at the time, refused to install anything else than an ancient C compiler. So it was a bit of inspired by necessity, but it actually turned out to be a great idea. If you don't have external dependencies, you can run anywhere. And people that do not have root on their Linux boxes, like everyone, can also install your system, which also turned out to be a great idea. DuckDB has APIs for lots of things. There's a list, doesn't matter. What is different is that people say we have APIs for a language so-and-so, right? But it's actually quite different for an in-process database, because if you have an API, say for Postgres in Python with this wonderful package that nobody can pronounce, it's very different from having an in-process database, because a database API just means it implements some part of the client protocol. But in our case, it means it runs the entire damn thing. So we have a JDBC driver for DuckDB. It bundles the entire system. It means that the driver actually contains the whole system. It's an interesting sort of mental switch to say, okay, it's all there. You don't need anything else. We found that in analytics, a wonderful file format called Parquet is really important to support. So because we don't like external dependencies, and we got into a shouting match with the people that make another Parquet thing on Twitter, we decided to just write our own. So we have written our own Parquet as a thing. I mean, at this point, I think it's one of the most powerful Parquet things that are out there. We like testing. I have to admit, after seeing the thing with the thing and the sound,
we don't have a game yet.
We don't. I see there's definitely room for improvement in our testing. Oh my god, I have never seen anything like that before, I have to admit. But we do think testing. We do like testing. DuckDB has hundreds of thousands of tests that are run on every commit. just for us to sleep at night. DuckDB is free and open source, MIT license, which basically means do whatever the hell you want with it. And for some reason, it has become quite popular. So at this point, we have beyond, I think we have 11,000 GitHub stars at this point since this picture was made. Thousands of Twitter followers, I think over 8,000 at this point. We've crossed 2 million downloads a month, which is pretty wild. And what's also really surprised me is if we look at the analytics of our website, right? Like we have over 500,000 unique visitors, not clicks, visitors per month on the website, which is, I don't know where all these people are coming from. Not sure what happened now. There we go. Maybe you have heard of this thing that there's also this company called MotherDuck now, which is a services company that makes a hosted version of DuckDB essentially. Offers a hosted version of DuckDB. So that's also going on there. They're doing like fundraising like crazy people. I don't really know. I don't really know about this. It's not really our forte. Or maybe I should say this. As opposed to MotherDuck, DuckDB and DuckDB Labs is not VC funded. We are fully bootstrapped, which means that we have to actually make the money we're spending. Okay, let me show you some things about DuckDB that I think is interesting to see. Here's a actually end-to-end example in Python where we import DuckDB. We create a pandas data frame. In case you have not heard of pandas, it's like tables for Python. Create a pandas data frame with 1 billion rows. And now we run a query on it, which is an analytical query because it just computes the average from this thing. And it will compute it, and it turns out that this will only take 157 milliseconds. Now the question is, why does this only take 157 milliseconds? Well, first of all, there's no cheating. We haven't like implemented a formula that computes the average on a monotonically increasing sequence and somehow detect this. And no. That's lame. No, we actually run this query on this entirely billion rows there. And how does this work? Why is this so fast? Well, it's because it's in process. Part of the answer, right? So DuckDB actually has native support and Pedro has been very hard working on that, to read a bunch of Python data structures, and where's Thijs? There. A bunch of Python data structures like these pandas data frames directly, basically without copying anything, right? We just like, you want us to query a data frame df here? Okay, well, let's look in the memory whether one exists. One exists, hey. We can query that and we can just run our scan primitives on that data frame. On top of that, we actually auto-paralyze this query. So you can see we have spent 1.2 seconds of compute on this query, which means because it's on this MacBook and we've just parallelized the hell out of this. This is how this comes to 157 milliseconds. Yeah, it's pretty cool. The same also works on the way out. So this is not in this example, but if I now wanted to say create a giant result set and move that back into Python land, we can also do some very efficient things, which is really nice. Yes.
And you create a data frame from it.
Yes, but it is one row.
Oh, okay.
Yes, SQL. The wonders of SQL. Okay, let's talk a bit about the internals. How does DuckDB work? So DuckDB uses something called vectorized query execution, and I'm going to talk briefly about that. DuckDB also uses something called modular parallelism. I shall explain. Two other things on this list: the push-based query engine and the out-of-core capabilities will be explained by Mark and Lawrence in a bit. So I will not talk more about this. There's also tons of other stuff. Mark has invented this bulk MVCC, which basically is a multi-version concurrency control scheme that is optimized for bulk changes to data as opposed to changing single values, which is like what you care about, right? Like you care about making a transaction. We care about, hey, an entire column has been added to this table, or half the values of this column have now changed. Do something about that. And it's a billion rows, by the way. Good luck. There's indexing that Tanya is working on. So if you want to talk about trees, we use this adaptive radix tree for the internal indexes, which is also an interesting question. And you, of course, wrote your master thesis on the question: do indexes actually have a place in analytical data systems, and how should they look like? Because it's not so obvious that this has to go together. Yeah, we have stolen / extended the Postgres parser for DuckDB simply because it's one of the most sort of widespread languages, SQL sub-languages if you want. And there's also some, as I mentioned, there's this homegrown Parquet. We also have homegrown object store IO, so if you have your data sitting on like S3, then we can talk to it using own IO layer, essentially. But let me talk a little bit about vectorized query execution and more sort of parallelism, unless that was in your slides.
No, go ahead.
Okay. So this whole idea of vectorized query execution, which was invented by Peter and Martin over at the CWI, which is not far from here, is based on this whole problem that the main memory reference is 100 nanoseconds and the L1 cache reference is a half of a nanosecond, right? And in order to make queries over large data sets fast, we have to somehow stay in this land and avoid this land. And you would think, why, it's main memory, it's fast. It's not the case. It's 200x faster, actually. It's slower, actually, than the cache. So how do you keep something that doesn't want to be contained in cache, like SQL queries over large data sets, actually cache resident? Well, using vectorized query processing. So first what happens is we split queries up in these pipelines. That's more interesting in the... Oh, sorry, I actually talk about... Oh, there's a mistake in my slides. Hang on, I shall fix this. Yes, there we go. Live editing slides, always good. So if we have the row at the time paradigm, which is traditional, which is what every system under the sun uses, like for example Postgres or Oracle or who cares. What happens is we have this pipeline here of different operators in our query. In this case, we have a scan from a table, hash join, probe, projection, and a group by. We will move individual rows of data between those operators, okay? This is great if you, for example, want to run queries like Postgres under a very tight memory budget, because, the buffers between these operators are going to be fairly limited. But this is really a bad idea if you want to avoid overhead, because if you want to do this on large amounts of data, because for every sort of switch between these operators, we have like cache invalidation between our in our instruction cache. We have function called dispatch, basically saying, oh, which function do I have to call? All these types are dynamic and I don't know them at compile time, I only know them at runtime. So I have a lot of overhead. So this is bad. Let's not do that. And if you look, and the reason why it's bad, another reason it's bad, if you look at one of these operators, for example, here just doing the projection, in pseudocode you can see that, okay, we read a row of input, they do an integer addition to compute this thing. It's just a lot of sort of dispatching, right? You have to figure out the types, you have to get these instructions and so on. And then you forget all of that and move to the next operator. So instead what we do, and that is really this is mentioned in this paper down here, the MongoDB X100 paper. So the innovation here is that we, instead of moving single rows of data between the operators, we move subsets, chunks of columns of rows between the operators. And if you look at one operator here, what it really does, it's kind of batching this up a bit more. So we read a chunk of input, and then we loop over this entire input and do the addition inside this loop, and then move on to the next. And that avoids the problems that I've mentioned, which is operator dispatch and function instruction cache invalidation. And that effectively allows us to keep most of this stuff. If we look at this again, it allows us to keep this entire sort of pipeline cache resident. Huh? That's really nice. Okay, but if you zoom out a little bit, we still have to sort of glue all these things together. So we have a fairly complex query up here. It's a standard aggregation query, and in order to actually parallelize this, we cannot. I mean, the vectorization helps us to make a single thread faster, but how can we do this on multiple threads? First thing we separate these queries into individual pipelines, where every pipeline starts with a source and ends with a sink, which is basically a blocking operator, which is an operator like a hash join in this case, or a group by that requires us to keep all the data, to collect all the data before we can continue, right? We cannot continue with the sort until we've seen all the input. So we separate them as pipelines, and then we actually parallelize inside those pipelines. So here we have the second pipeline of this query I showed you before, with the scan, the hash join probe, the projection, and the group by build, which is the blocking operator. And what we do is we basically just duplicate the streaming part of these pipelines, which is these three operators down here, as many times as, for example, threads that we want to run on. And then we glue the intermediate results back together in this group by build up there. And that's a bit more complicated because now the operator actually has to know how to deal with parallelism, which means that in every operator we have to think about how do we actually combine the results coming from, first of all, how do we keep parallelism alive, but how do we actually also combine the results coming from these individual streams into the final result that we hand over to the next guy. That's in a nutshell how the Morse over parallelism works. It was mentioned before, there's DuckDB extensions. I want to talk about those briefly because it's like the way how we see the ecosystem growing at this point, because we don't think we're going to add a million more features to DuckDB itself. Rather, we think we should, all the sort of the growth in sort of really crazy features should come from extensions. And we have actually a fairly sort of streamlined way of doing extension installation. So you can just type in SQL, you say install, for example, JSON. I forgot JSON here, sorry. Don't know how that happened. I think probably because it's in tree. So you can just install JSON and we'll actually fetch a dynamic library from the internet for your platform, load it into DuckDB, and then you can load it with this additional command here, and you can start using these features like new functions, but you can also add new file systems and so on and so forth. We even have a complete abstraction for the storage, so you can have your own storage extension that provides a backend for an entire type of table. So you don't have to, use our storage. You can also just plug everything here. There's a ton of existing extensions. For example, Max has been working a lot on a geospatial extension, right? Which is how do you manage data that has coordinates, geographic coordinates in DuckDB. That's an extension that you can load, and suddenly you have new types, you have new functions, you have a lot of new stuff that you can just use from that on. We have HTTPFS as an extension. It's really annoying. The reason HTTPFS is an extension is because to do HTTPFS you have to use OpenSSL, and OpenSSL is a gigantic monster that you don't want to ship as part of your binary, so you have to link, but we don't have dependencies, so therefore we cannot do that. This is why we have an HTTPFS extension which actually statically links OpenSSL, and you load that extension if you want to do that. We have an extension that supports that helps you do Arrow, which is this in-memory interchange format for tabular data. We have an extension to read Apache Iceberg files, which is a sort of up-and-coming open storage format for tabular data that supposedly supports transactions. Yeah, this is wild. There's ICU, so if you want to use like crazy time zone math in DuckDB, we don't, for obvious reasons, we don't, bundle the whole, 30 megabyte or so of ICU with DuckDB by default, but it's an extension. There's the SQLite and Postgres scanners. They're kind of funny because they allow you to read, for example, SQLite tables from DuckDB. And a fun fact, we can do this faster than SQLite itself because we can actually parallelize the damn queries and they cannot. Same for Postgres, by the way. We have support for things like Substrate. Azure support is coming. AWS integration, where just basically being able to talk to the object stores. JSON, like there's tons of this. And it's been mentioned already that indeed the extensions are something where we are super interested in making it possible for other languages to write extensions in, because that's possibly reduces the threshold for people to start writing extensions. Yeah, and that's more to come. And now somehow my thing is stuck. I hope that's the last slide. That was the last slide. So that's it. Thank you.